Earthlings and explorers of all ages. Welcome to Ask an Astrobiologist, the show that celebrates the science and the scientists involved in our quest to understand the nature of life. As always, I'm your host, Dr. Graham, the cosmobiologist Lau, and we are brought to you by SegaNet.org and the NASA Astrobiology Program. Now, we've been doing this show for quite some time, and we always love every month to point out those of you out there, institutions, people, profiles in social media, all kinds of things, where you're sharing about our show, you're engaging with our guests, you're talking about astrobiology, you're asking questions about astrobiology and what we know about life in the universe. This month, we want to give a special shout out to the Arizona Astrobiology Center on X. That's at AZ Astrobiology. Thank you so much for sharing about our show and our awesome guest we have joining me here shortly on this month's episode. For all of you out there, if you share about our show, we might give you a shout out, and I might just be saying your name next month or in some month coming up here on the show. So please, as always, thank you so much for sharing about our show. We really appreciate it. Now, today's episode is going to feature a conversation that's going to take us through a range of topics, from the inner solar system to the outer solar system, from dinosaurs in our ancient past to exoplanets very, very far away. Joining me today, we have Dr. Jessica Noviello, a postdoctoral management program fellow at NASA's Goddard Space Flight Center. Jessica's research career has included studies in a variety of topics, so many it's actually kind of hard to think about for me. She's done work in a mission concept for Venus, on asteroids like Itokawa, moons, surface features on moons like Europa and Pluto's moon Charon, studies of dwarf planets like Haumea, and even research on the detection of potential biosignatures, signs of potential life on exoplanets from so far away. So we have a lot of fun things to discuss, and we also want to answer your questions as well. So for those watching live, please ask your questions in the chat. But first, I have the chance to chat myself. So Dr. Jessica Noviello, thank you so much for joining me for Ask an Astrobiologist.
Thank you for having me, Graham. This is so much fun to be here. Hi, everyone.
Yeah, I'm so excited to have you on the show. We've been thinking for a while of having you on, and honestly, I will admit I knew of some of the things that you've done. I didn't know how many different things you've studied, and so we have a lot of stuff to talk about. We have asteroids, Pluto and Charon, Venus, a bunch of stuff to talk about. But before we get there, with all of our guests we have on the show, we really like to know what got you started in science, in astrobiology, in planetary science. What was that first thing that grabbed you and made you want to pursue a career in this direction?
Oh, that's such a good question. And I have what I consider an atypical kind of origin story then, because I wasn't a kid who grew up looking through telescopes and wondering about the stars in the night sky. I grew up with my eyes very firmly planted to the ground. And when I say that, I mean, I was really interested in dinosaurs from a very young age. And I think a lot of kids, they go either space or dinosaurs. And I very clearly went into the dinosaurs route. So I was really obsessed with dinosaurs. I loved everything about them. I loved wondering what they looked like, what they ate, how they interacted with each other, what their environments were like. Anything dinosaur related, yeah, I was very much known for that. And even today, people are like, oh yeah, Jessica, she likes dinosaurs in space. So it wasn't until my junior year of high school when I was looking for a nonfiction book to read for a summer reading assignment, and I came across a book that talked in detail about the asteroid hitting the Earth at the end of the Cretaceous period, so the KPG extinction event that we know it today. And I loved dinosaurs, but here was this thing that was destroying the non-avian dinosaurs, and oh, that's really interesting. What is it about this asteroid or any asteroid that makes it? I don't know. I was really intrigued by this thing that was more powerful than the dinosaurs. You know, what is it about them? So I started getting more into that, and then started looking into when I got to college, and I was a double major in physics and earth and planetary sciences, and I specifically started taking planetary science classes, which I hadn't known was a field. But it makes sense. Like, who are the people who study the rocks in space? Oh, yes, they are planetary sciences. But again, too much dinosaurs, or maybe not enough dinosaurs. I don't know. We could be the judge of that later. So started taking all these planetary science classes, learned about potentially hazardous asteroids, which are still potential threats to our own survival, and just got into planetary sciences from that perspective.
I love that so much. You know, there's this thing that you love as a child, and then you find out something destroyed it, and so you want to know more. That's pretty cool. And, you know, really, I mean, the study, you know, of the history of us studying asteroids and planetary impacts is truly intriguing. You know, from the Alvarez paper from 1980, you know, through all of our studies to discovering the Chicxulub crater, the impact crater, to, you know, even current research, we're still learning more about what led to the demise of the dinosaurs and the end Cretaceous era. And so it's pretty cool. That's the kind of your intro. And I think you're right. For a lot of kids, it's dinosaurs and space. Like, those are two super intriguing things. And a lot of us in astrobiology, we kind of get to do both in some ways. We study life and we study space. And so that's kind of fun. So before we kind of get into some of the more current research you're working on, your research pathway has taken you through a lot of different studies, like I mentioned in our intro, from the inner solar system, the outer solar system, and beyond. I want to start off with asteroid Itokawa and some of the work that you've done on Itokawa, and what your research has been on this very intriguing asteroid.
I love Itokawa. It was the first planetary science body that I ever studied, so it holds a very special place in my heart, as this is where I began, effectively. So I was an intern at the Applied Physics Laboratory up in Laurel, Maryland, and I had wonderful advisors who I feel like kind of took a chance on me, because I was still not really sure what I was doing. But I guess that's true of many interns, right? We all start somewhere. And these mentors were Olivier Barnewin and Carolyn Ernst, fantastic people, and they had me work with them for a summer. And my job on Itokawa was to count rocks. I kid you not. But it was we used a tool that had actually been developed by software engineers at APL, and it was a fascinating tool. So, okay, I should describe what Itokawa looks like, because it's not a spherical rocky body. It doesn't look anything like Ryugu, where the Hayabusa 2 spacecraft went to. It doesn't look anything like Bennu, where the OSIRIS-REx spacecraft went to. It, depending on who you ask, if you are a Japanese space scientist, you say it looks like an otter, but I think it looks more like a manatee. But Itokawa actually looks like there's a head, and then there's an oval body, and they're stuck together. And that's actually how we refer to the different parts of Itokawa, as the head and the body. So it does rotate upside down, or what we might look at upside down. So I guess it is more like an otter, but you know what? Otters are very cute too. So, I was looking at all of the blocks on this asteroid. And by blocks, I do mean rocks, and but they range in so many different sizes. On Earth, we have many different names for rocks. We have pebbles, we have down to sand, we have boulders. But on Itokawa, we just generically called them blocks. And the point of doing this, and doing this for different areas of Itokawa, is we were trying to figure out how the surface has changed over Itokawa's history. So over time, rocks or blocks on an asteroid surface, due to thermal, just thermal stresses and different micrometeorite impalements and bombardment, the rocks will start to break down into what we call regolith, which is kind of like dirt on Earth, except it doesn't have organic components like we would have in soil here on Earth. And on Itokawa, because it's so small, it's only about 500 meters long. So maybe I think that would be something like 1.6 football fields if I had to do a very quick conversion in my head, but it's not a very big asteroid, and its gravity is very small. And even so, the pieces of these rocks that are breaking off, they are migrating down to these points of lower elevation where the gravity is relatively strong. So we have these low points, we have these high points, and we were looking at the blocks in these different areas to figure out using some math about how the surface has changed over time. So that was my very first planetary science project, was Itokawa's surface evolution.
That's very cool. Now, I will say, I've always heard it looks like BB-8, the robot from Star Wars.
But I was doing this work in like 2013, so BB-8 hadn't been invented yet.
Fair. Okay, that's awesome. I was walking with my 4-year-old child at a local lake recently and trying to talk about the difference of sizes of pebbles and boulders and things like that. And I held one up and I'm like, is this a pebble? He's like, that's a stone, Daddy. So maybe we're not quite there yet. But then we as humans are still learning a lot more about these different kinds of rocks through the evolution of the surfaces of asteroids like Itokawa and more. Now, like I said, there's a bunch of topics to cover, and so I do want to jump around a little bit here. I'd love to hear about this concept mission that you were working on related to Venus. I love Venus. I always tell people that if there was any other world in our early solar system that likely had life, it seems like it would have been Venus, if anything. Can you explain more about the mission that you were involved with, this concept design you were involved in?
Of course. So this was a mission that I designed as a part of the JPL, that's Jet Propulsion Laboratory Planetary Science Summer School. And I did it in the year 2020, which, as we all know, is not like any other year in that we can remember. So we were doing a lot of things for the first time, doing them differently. And this group of 18 of us postdocs and grad students, we got together and we were told, okay, you have 10 weeks basically to work on this mission concept. And we got training from JPL people and engineers along the way. We had some fantastic mentors who showed us step by step, this is what you need to do to build a NASA mission. And there were lots of things that we learned about, like the science traceability matrix, which every mission is governed by a science traceability matrix, which is the nitty-gritty of how you get from the big picture science goals of where is life in the solar system, getting down to exactly what measurements in what range you're going to take and with what instrument. So it's critical for a mission to have this. And that was just one of many things that we learned. The mission concept that we decided on as a group and then built as a group, we went to Venus, and this mission is so cool. It was called Valentine, which is the Venus Air and Land Explorer Novel Trailblazer for In Situ Exploration. So it's quite a long acronym, but the whole point of this mission that was so different, we weighed doing an orbiter mission, which wouldn't get anywhere near the clouds, and we weighed doing a lander mission, which would land on the surface, but wouldn't last very long under Venus's pressure and temperature conditions. And we said, well, why don't we just hang out in the clouds? So we have this Aerobot mission, which is basically a giant balloon that just passively floats through the clouds, and it takes dips. How many did we have? I think we had something like 5 or 6 dips between 55 and 45 kilometers, and just trying to get beneath different windows, get different profiles of the clouds in different latitudes and longitude on Venus, and hopefully get at questions like, when did Venus's oceans disappear, which we could understand if we knew more about different isotopic ratios in the clouds of Venus. So that was one of many topics we wanted to discuss. So I loved the Valentine mission. It was such a fun experience working with that team and everybody who was on it. So much love to Venus.
I love it so much. Yeah, Venus is one of my favorites of the solar system. Of course, though, this is Ask an Astrobiologist, an astrobiology show. We have to talk about another major friendly or fan place for astrobiology, which is Europa. You've also done some work on studying the features on the surface of Europa. I wonder if you can speak about your own research there and the importance of understanding the surface of Europa, especially.
Sure. So that was actually my entire PhD dissertation was on Europa and Europa's history. But I was specifically looking at the what I called microfeatures. These are small scale features on Europa's surface. And when I say small scale, I still mean like 10 kilometers in diameter, but I didn't want to go for the massive chaos features that so many people had studied before. And here's a fun technical term. So when I say icy chaos, for anybody who hasn't heard that term before, it's a feature specific to Europa, and it comes in a couple of different forms. So some of these places look like sandpaper, and other places look like you took a mirror and you just broke it on the ground and all the pieces rotated, but they're fractured, and you can see that there's the icebergs, which would be the shards of broken glass, and then there might be the floor underneath it that might have more of that sandpaper-like appearance. And people have looked at these features and they say, wow, they come in different types or morphologies, they come in different sizes. I wonder how they formed. And this has been a big debate for decades in Europa science is how did chaos features formed? So I looked at the small scale features, and I mean different, there's chaos included in there, or micro chaos, which is just like the big chaos, but at smaller scales. But there's also pits, so depressions in the surface. There are domes, so like a hill on Europa's surface. There are these dark splotches that don't have any kind of obvious topography, and we called them spots. And then there were these hybrid features that kind of looked like a dome and chaos put together. So it was maybe like a dome, but it was surrounded by that sandpaper-like texture that you might associate with the chaos. So I looked at all of those. I looked for different geospatial patterns in this work, and that was the cool thing that I did was I brought in geospatial stuff from Earth tree ecology, actually. There was a Clark and Evans 1954 paper I cited all of the time that talked about the density of different types of trees, and I just used that to study the different densities of microfeatures on Europa. So that was part of my work, and I was doing that to try to test hypotheses that models had put forward. So, and these models were basically, how did these features form? And if they formed this way, then we would expect this kind of geospatial pattern. But if they formed this other way, we would expect maybe a more dispersed pattern or maybe a more random pattern. And I can't say that I have solved everything because nobody has solved everything, but I do have my favorite theory, at least that is supported by my own research.
Oh, very cool. Yeah, I think, a lot of us talk about Europa and its potential for maybe a biosphere in its deep ocean down below that icy crust, but there's so much more for us to understand about the surface processes, near surface processes, and the connection of that surface down to the ocean down below and what that connection might even look like. And so exploring those features is so crucial to that. Now, I do want to move on a little bit more yet, while I still have my chance to talk with you alone before I open it up to our audience questions. You've done work, in Venus and Itokawa with asteroids and Europa, and we've had, guests on the show previously who've talked about these various kinds of bodies, the traditional things we think about in astrobiology and solar system exploration. But you've also done some work on the dwarf planets of our solar system, which we haven't actually spoken about as much on the show so far. In particular, Haumea, you've done some work on, and we've never talked about Haumea on the show before. And so before I ask you a question here, I do want to share that we polled our audience online to ask them what is the most unique thing that stands out about Haumea right away. And most of this comes from just like looking into like a Wikipedia article or looking online. But for those who look it up, they're going to notice a few things. We offered some possibilities like a large size or having a subsurface ocean, but it really is the peculiar shape this weird elongated shape of Haumea that really is kind of intriguing for people when they first learn about it. Now, I'd love to hear more about your own work with Haumea and this unique body in our solar system.
The triaxial ellipsoid shape of Haumea, as you know, the technical term for basically it's a deflated American football. So I that's definitely one of the things that's very odd about Haumea is how did it come to get that shape? There are so many weird things about it, though. It rotates incredibly quickly. It's just over a 4-hour rotation period, which for an object as big as Haumea is incredibly fast. It's actually the fastest rotating large object in the solar system. Say that 5 times fast. So it's also got a ring system. It's got 2 moons. It also is dynamically associated with many other objects, at least a dozen. So this is the first dynamical family in the Kuiper belt ever identified. And there are a few of these dynamical families in the asteroid belt, but only one so far in the Kuiper belt. So that's kind of interesting too. And why is its surface completely covered with water ice? And there's also a red spot on Haumea that might be organics. At least this is what people have said that they are, but it's not ever confirmed. And it's so small. It is large, but it's really far away. So it's really small when we look at it through a telescope. So it's really difficult to study Haumea. So we have to make a lot of allowances when we study it and when we're trying to model it. And this is what my work did. So we published this last year, and it was a long paper. It is a long paper, and I'm sorry for those who will read it, but there are a lot of figures, so it makes it a little bit easier to read. But there are so many cool things that we discovered about Haumea. One is that as Haumea was growing, or at least changing size, its core and the size of its core and the density of its core actually drove a lot of its formation. So what we proposed happened to Haumea in this work is that as the core was growing, its rotation rate was changing, and actually it was even faster when Haumea was younger. It was actually spinning faster, and it was spinning so fast that material flew off of the ends and eventually coalesced to form the moons and the ring system that we know today. So that is one of the ideas that we put forward into the literature, and we said, hey, we think we know what happened to Haumea. So that was one cool thing that we found. And we did a lot of that using a geophysical code called Kyushu, which was developed by my collaborator, Steve Desch. And then we used a different code called Icy Dwarf, which was written by my other collaborator, Mark Navu, who's also here at Goddard. And his geochemical simulations actually revealed that Haumea was, in its youth, warm enough to sustain a liquid water ocean. Now, it wasn't a very long-lived ocean. It was about 250 million years, or about 250 million years, but that's still a pretty long time. That's like between now and like the end Permian extinction, which is even before the dinosaurs. So just bringing it all back to dinosaurs in the end. And so that I thought was really cool, is that, wow, Haumea might be an extinct ocean world. And that's really cool, because that made me think much more closely about what is it that we consider ocean worlds in our solar system, and what is or isn't, and do we consider things past and present? Where do we look for? Now, I want to be very clear that I'm not saying Haumea was inhabited. I am saying that the geochemical modeling we have done, and its size and its composition that we can tell, suggests there was a subsurface liquid water ocean. So I thought that was the coolest thing. And then if you talk to Steve Desch, he will probably say Haumea was really cool because it helped put in perspective the timeline of the outer solar system and the dynamical history there, putting more constraints on things like Neptune's migration and even Triton's capture. So there was a lot going on in that paper.
Love it. And that's kind of also a question I had then, since we don't really talk about dwarf planets so much for astrobiology. I was curious, how do you envision understanding the dwarf planets and kind of helping us better understand the nature of life? Do they help us better understand like the history of formation, the structure of solar systems, the delivery of materials to worlds? How can we kind of, see the dwarf planets as being important for astrobiology studies?
Mm. I think for me, they represent this very critical in between point of not quite a planet, but not an asteroid either. So they have odd aspects of both of them. And one of them, especially out in the Kuiper belt, where most of the dwarf planets are, or at least the ones that we know of so far, they have a lot of organics and a lot of water. And this is just a reflection of how we think the solar system actually formed, is things way out away from the sun had ice, and the things inside the water evaporated. So they are like asteroids, fossils of an earlier time in solar system history, but I think like planets, they have a lot going on their interiors, or at least they used to. So studying, they're a key part in a continuum of how worlds grow. And as worlds grow, if there is a biosphere, how does that biosphere respond to it? So I think just understanding where planets come from is a very fundamental step in understanding within context astrobiology in our solar system.
Fantastic. Now, before we move on, so your 2022 paper, it is long, as you say, but I hope that our audience will go find the paper and read it. I also know that you wanted to mention something important about the artwork that was developed for the cover of that paper. If you can speak to that for our audience.
Yes, thank you for bringing that up, Graham, because there is a figure, and it might be the first figure in the paper, actually, and it's a six-panel illustration of of our formation hypothesis for Haumea. And this was developed by a woman at Arizona State University named Sue Selkirk. And I am so sorry to report that just last week, Sue passed away. And she was so instrumental in doing artwork, not just for my paper, but for many papers that people in the department put out over the years. She was responsible for so much original artwork that is still hanging up at ASU. She made sure posters got printed and got to their conferences on time. She was so key for what we did in our department, and we're really going to miss her. And I just wanted to make sure that her memory is honored, because she really did so much good work.
Yeah, I love that so much, and thank you for sharing that with us. I think it's important for people to know that what we do in space science, in astrobiology, planetary science, it's not just the science and the engineering and building the missions. It's the people who create artwork, who help us, who do administration, who do business, who do all the things that are necessary for us to do this endeavor, this process of science, of learning more about our place in the universe. And so I'm so glad that she was involved in your own career and in developing artwork to help better our knowledge of space science across the board. Now, we're going to move on just a little bit more here before I open up the audience questions and we do our Faster Than Light segment. There's just so many cool things that you've worked on. I can't help but ask about a whole bunch of different things. Now, more recently, you've been doing more work on exoplanets, specifically looking for biosignatures on exoplanets, or potential biosignatures. What kinds of signs of life specifically are you interested in finding or looking for on worlds around other stars?
Once again, my answer is going to come back to dinosaurs. So now dinosaurs and exoplanets, where the heck is that overlap? It comes down to, I wonder if I should bring this up now. Ooh. So when I was a grad student in Arizona, I got very involved with a paleontology group, and this group actively goes out on digs to different parts of the Southwest, and I still get to do that even though I live out in Maryland now. I just make a special trip once a year to go out on this dig, and I was just thinking, like, wow, I wonder if, like, what is the connection then? Like, why does my brain work this way to what am I missing? Like, I don't know. I love to build connections and bridges, so I was thinking, oh, there has to be something here. And I was talking to one of the paleontologists on a dig once about mass extinctions, because that's how I got started in planetary science. I just thought it was really cool. And he was wondering, why is a NASA scientist doing a dinosaur dig? So we talked about mass extinctions, and then I started thinking, well, if mass extinctions, of which we know at least five in the fossil record here on Earth, well, maybe mass extinctions are a part of life. Maybe if there's life elsewhere in the universe, maybe they are also experiencing mass extinction events. And if they are, what might that look like in an exoplanet's atmosphere? How did Earth's atmosphere respond to the level of biomass decaying at the end of something like the KPG extinction event or at the end Permian extinction event? And are these signals detectable? And since they're more like signals of death than signals of life, we've been in our research group calling them the necrosignatures. So I'm really excited to see where this work goes. This is very much still in its early phases, although I have presented on this work at conferences, and I have a couple of abstracts out on it now. But I feel like there's something here. And again, coming with the mind of somebody who has a space and a dinosaurs background, I feel like this is a problem that is really intriguing, but also kind of made for me to tackle. So I'm really excited to see where this goes. And maybe it doesn't go anywhere, but at least I tried.
Yeah, and it's still a very intriguing idea. We often think about possible signs of life on exoplanets, and people think about, like here on Earth, like photosynthesis, production of O2 being in an atmosphere with things like methane and other molecules. We've had guests on the show talking about potential technosignatures, like signs of industrial activity on exoplanets. But we haven't really talked about the potential for mass extinction and large-scale decay of biological material on a world and what that might look like. So it's really intriguing research. I'm excited to read more about it when you do publish and put more out there for us to explore. Maybe in the near future, we'll have you back on the show to talk about maybe a potential discovery of a necrosignature. Now, I do want to move in just a little bit more to a few other things before we open it up to our audience. First off, you mentioned earlier that you've done an internship. You were part of this planetary summer school at JPL. You've been involved in various realms of your own career, kind of exploring options of what someone can do in their career. And we really want to point out that you've developed this thing called PAWS, or the Professional Advancement Workshop Series, where you've been kind of leading these seminars for helping people not just learn about, what is the action of becoming a planetary scientist or an astrobiologist, but, how do we develop our careers once we're here? I wonder if you can speak more about the impetus for developing this workshop series and what it's meant for you in bringing this to others.
I would love to. Thank you for letting me speak on that. So PAWS was inspired very much by my own frustration. And it was 2021. I had fairly recently started as a postdoc at Goddard, and I was already thinking about, okay, what do I do after this? Because any academic will know you always have to look like 3 years ahead to figure out what your next step is going to be. And I was sitting in my room just thinking that I don't know what else is out there. And we had always joked, or at least my friends and I had always joked, like, oh, if academia doesn't work out, we're going to go into industry. We'll do data science. It's fine. I already have that skill set. But do we? Like, what is that skill set? And if we're lacking things, how do we get from A to B? And what do we need to do now to prepare for that down the road? So I didn't know the answers to these questions. I didn't know what else was out there. I had a PhD, but what did that mean? So I figured to myself, if I was asking these questions, then maybe other people are asking these questions. And maybe this is something that the community can come together on, and maybe we can learn together. So I pitched an idea that eventually became PAWS. I first pitched it to my advisor, Sean Donegal-Goldman, who then told me to contact Melissa Kervin-Brooks, who then brought it up with Mary Wojtek, the then head of astrobiology. And we did get some funding just so that we could bring in outside speakers. So, the point is, if we're looking for careers that aren't just NASA researcher, then we need to look to people who are outside of NASA. And to do that, a lot of times you do need money so you can pay people for their time. So we had some seed funding, and we were told, do this for 6 months and we'll see how it goes. And we've been doing, that was August 2021 when we started. So now we're more than 2 years past it. PAWS is now a community of 500, mostly early career scientists, but also some senior scientists who are just interested in the kind of work and what kinds of options are out there. So we've talked about all kinds of things like data science, of course. We've talked about jobs in NASA management. We've talked about jobs in even video game design and what that might look like for somebody who's a scientist to move into video games. So most of our work is recorded. And there is actually a website where anybody who's interested in learning more about PAWS, you can go and you can look and you can watch most of our videos of our recordings from our PAWS events.
That's awesome. And I'll share that website right now. It's nexus.info/PAWS. It's nexss.info/PAWS for those who want to look it up, learn more about it, and maybe learn more about professional development for those of us kind of in the realm of astrobiology, but also in planetary science, space science, other realms as well. And I'll say for myself, having decided not to pursue the traditional academic pathway, there is a lot I had to learn along the way, and a lot of it was teaching myself a lot of skills that I was never taught otherwise. Mm-hmm. And so it's important, I think, for us to kind of have those experiences to learn about ways of finding new career ventures for ourselves. Oftentimes I've heard people lament they're going to quit their career and open a bakery. And I'm like, do you know how hard it is to run a bakery? That's actually a lot of work. And if you don't know how to bake something to start with, maybe that's not the career choice you want to make just yet. But there's a lot of options out there for careers. I know a lot of people watching our show are interested in career paths in astrobiology, and so it's great to know that there's not just one single track. There's lots of different directions our careers can take. Mm-hmm. Now, besides just giving back in this realm of career advancement,
Graham, I wonder if I could just say like one more important thing is that one of the things that I wanted to do when I created PAWS is to focus on developing transferable skills, because people can love science, but they reach a point in their job where they say, this isn't working for me anymore. So I did want to make sure, like you said, that there's flexibility in what people can do that still keeps them in science, because I firmly believe that everybody belongs in science. If you want to be here, there is a spot for you. The trick is finding where that spot is that makes you also feel fulfilled and complete. So that I focus on that when I'm trying to put together the next PAWS event. And hopefully this is not the end, and we'll just keep going.
Awesome. I love that so much. And hopefully there will be a continuation of it for many, many years to come for others who need to learn these skills. Now, before we go to our Faster Than Light segment, a couple more things I do want to point out that you and I, in the not too distant past, did a Twitch stream together on our friend Monica Vidari's Twitch channel at Astro Traviesa, where we talked about planetary science while she played a game, which was kind of fun. As those who know me know, I've done a lot of community engagement and trying to share the science of astrobiology in various channels in various ways. You've done a bunch of work in this realm yourself. I wonder if you can share with us kind of your vision of why it's so important to do things like community engagement, to share our knowledge of science through various channels like video games and other things like that.
I think it comes back to my core belief that everybody has a place in science. And even if it's just as somebody who is a very enthusiastic observer who's like, you know what, like I'm more... I don't want to do the science, but I want to support the people who are doing the science. And I also feel, as somebody, we often hear this like, oh, your tax dollars support science, and it's something that I keep in the back of my head of like, this is me giving back to the entire American community of trying to explain what I do and why it's important and why it matters to keep funding this kind of work. And so I'm not going to get on that soapbox, but I feel like I'm just paying back a lot of what has been given to me. And plus, it's just a lot of fun to do things like Twitch streams and to put out Instagram posts with beautiful visuals. And people like to hear about it. People like to know more about it. We're all wondering what else is out there. And I get to be somebody who can answer, maybe like 1/1000th of that question, but I can still help. And if I can help people engage more with science and be a little more full of wonder in their own lives, then I'm going to try and do it.
Fantastic. Yeah, I love that so much. I do have to move the show along. I noticed that we are running out of time for all of our viewers to ask their questions. But before we get there, we're going to have our faster than light segment. These are just some very fun, short questions we ask of all of our guests to kind of have an idea of different astrobiologists and kind of their view of some of these topics. The very first one comes from Enrico Fermi's famous question of where are they? Why aren't there aliens here right now? If faster than light travel is possible, why aren't there aliens here right now? So, what is your favorite answer to Fermi's question, where are they?
Oh, I think they're out there. And they are probably wondering the same thing as we are. And where are they? I don't know if I can point to a planet and say, like, oh, they're on TRAPPIST-1e. Like, it's not going to be as precise as that. But I think the coolest things that we're going to find are probably in the deepest parts of our ocean and extremophile organisms that are maybe bubbling away in Yellowstone's lakes. Like, again, those are not aliens, but they're going to be alien-like. And where are they? They are, I don't know if this is quite an answer, but they are out there and they are wondering the same about us.
Groovy. I love it. So one thing that I've noticed in hosting this show over the years is that all of us in the realm of astrobiology have been inspired by some kinds of stories, from books, comic books, movies, television shows, video games for some of us. So what stories have inspired you to want to learn more about life in the universe?
The KPG extinction event. No, I remember, like, as a kid, I was watching the BBC documentary of Walking with Dinosaurs, and that really kicked off my love for dinosaurs, which opened my love for science. So I feel like in my mind it always starts there. And then, of course, I've already explained how it got to how I started learning about asteroids that way, and it's just opened up everything else. So I remember doing bad science movie nights with my friends in grad school. We did watch a couple of space movies, like we did Europa Report, and you know what? It was fun to be in a room full of scientists while watching that movie. I think I'll say that.
Love it. Yeah, I mean, I've watched a lot of fun movies that are known for their lacking science, like The Core and others, that it's just fun to watch, to explore those ideas and what's right and what's wrong in some of those films. Now, having developed PAWS, you've spoken to a lot of people about career development, career advancement, different ways to build and develop your career. But if you could go back in time to the beginning of your career and give yourself advice, what would you say?
I'd say the same thing I should tell myself more now, is that you know what you're doing and you can trust yourself. And just believe that you know what's going on, and speak your mind, and remember that you too are the expert and you can speak up. So yeah, just trust yourself. And for everybody out there, trust yourself.
Yeah, I love that. So you have the expertise to be a very good person to answer this next question. We don't always get an answer to it because it makes us pick a side. If there is alien life out there, do you think we're first going to find it in our own solar system or on an exoplanet?
I feel like I have to preface this by saying this is my opinion, but I think we have a higher chance of finding it within the solar system, just because it's closer. We have more tools because it's closer. We have more tools available to study what is in our solar system more than we can study what is on an exoplanet right now. Exoplanets are plentiful. They are incredibly numerous. We have cataloged something like over 5,000 of them at this point. But we will never, or at least not in my lifetime, we will never see the surface of an exoplanet the way that I can look at a picture of Europa's surface or Mars's surface or even Pluto's surface. So I think just because even if we have fewer data points, we have better data points in our own solar system.
Very cool. My last question, and it's my favorite of them all. What is an unbelievable science fact that still blows your mind?
This one, it's so cool. Okay, so Europa's surface is incredibly young. And there's a lot of, we can tell that just because there aren't many craters on it. And we generally use the rule of thumb, like more craters equals older surface. And there is a quantitative relationship between that. So we have estimated the age of Europa's surface to be between 80 and, or between like 50 and 180 million years old, which means that there are dinosaurs, and it might even be a majority of dinosaurs, of their fossils that are older than Europa's surface. Not that they ever looked at Europa, but there are some bones that are older than Europa, and that really blows my mind of putting all of the solar system's history into context.
Yeah, I love that. It's one of those things where it's like, space is closer to you than you are to most other people on the planet. It's one of those kind of things where it's like, if you hold a fossil of a dinosaur, it's very likely older than the surface of Europa, which is one of the key surfaces that we're studying for astrobiology. So I love that so much. Thank you for those answers to our faster than light segment questions. We're now going to open it up with the time that we have left to audience questions that are coming in from the chat. We do have a lot of them, and so I'm going to try for everyone who's asking questions to get through them as quickly as we can. It sounds like a lot of folks have really interesting questions for you, Jessica. First off is a question from Dr. Jim Pass, who often likes to ask questions about sociology and the humanities involved in astrobiology. He says, in your status as a science communicator, how would you approach emphasizing the importance of the discovery of living ET life, extant ET life on Mars or Europa as two examples, especially to those who argue that astrobiology and space exploration generally are a waste of time and money? Ooh, it's a two-part question.
Okay, I'm going to need 30 seconds to think about that. I would say that if scientists are going to announce the discovery of life, we need to be 100% sure that what we are looking at is actually life. And this is something that many of my colleagues are working on, the standards of evidence. And if you were to Google that, I'm sure you would find that also very long paper about how do we know that we're looking at life? And that is not an easy question to define. If we went to Mars and we looked at a rock and we saw microbes crawling on it, that's pretty definitive. But for most of my colleagues who study exoplanets, that's not realistic. And so I would say, first, we would have to be 100% sure. And then we would, as a science communicator, I would still be very hesitant to say anything definitive. For the people who say that science is a waste of effort and time and money, I have heard that. And my answer to that would be that science and the exploration that we do of space is so much bigger than just the money that we put into it. It's hard to say what value inspiration has, or rallying around a science question like we see the community do, and even seeing nations like in the 60s when we had the Apollo program here in the United States, we really had a lot of sentiment around that mission. And that it's hard to put a value on something like a monetary value on something like that. And I think there's a lot of potential to bring people together into a bigger and work towards a bigger question and a bigger purpose. And that is something that space can do like very few other things can.
I love that so much. I probably should have saved that for the last question. That was such an important answer, I think, for everyone. I'm going to preface our next question by saying that, so as Dr. Noviello knows, we have very limited high-resolution mapping of the surface of Europa so far, of images of the surface of Europa. It's going to get better with Europa Clipper, but so far to our knowledge, there aren't many great places for a nice flat landing, for instance, on the surface of Europa as of right now. There was a Europa lander concept mission some time back that tried to determine where would we land a lander on Europa, and so having the Clipper go will be very important. But that leads us to this question from Sangeet Demon. Sangeet wants to know, based on your work on microfractures or microfeatures on the surface of Europa, what are the importance of these microfeatures and implications for finding a landing site for a future mission to land on Europa?
That's a great question. So one of the things that I looked at specifically that was very critical to the models that I was testing was the pits. So they're the depression features. And one of the cool things about pits on Europa's surface is that they tend to cluster with other pits, and they also tend to be closer to other features in general, like ridges. And this was something I was working on right at the beginning of 2020, so I still have yet to go back to it. But so these features, if they're clustering together, then that is a pattern, a larger pattern that we might be able to see even in our low resolution imaging. And you might want to avoid a place that has, a lot of depressions, because then if you land on a slant, it might not fall over, but it might fall over, and then you don't have a lander mission anymore. You have like a tumbling mission that might land upside down. So, what would be the best place to land on Europa? That's really tough, because you don't necessarily want to do it in the middle of a chaos feature, especially if it has that sandpaper-like texture, because, it looks small, but they're actually quite big bumps and ridges. I would really like to land near a ridge, actually, on Europa, or one of the cycloid features, because I think whatever formed these ridges and these features prevents other features from forming too close, which means there's a little bit of space on either side of the ridge where it might be a safe place to land. And then you can get probably some really interesting seismic data. So again, I'm not telling NASA what to do, but I would be really curious to see what it was like physically next to a ridge.
Very cool. We have a question from Sib Sankar Palit. Sib Sankar, by the way, works with me at Blue Marble Space Institute of Science as a visiting scholar. He's been working on the light detection knowledge base, part of the Center for Light Detection. He has a question regarding the upcoming Venusian missions and what you think of their potential astrobiological or their astrobiological potential for helping us better understand Venus, probably including the potential Rocket Lab mission, but also other missions that are being planned by NASA, ESA, Roscosmos, and others.
So I think the most important thing that we can get from any of these missions, and it might just be because I'm at Goddard, which is running the Da Vinci mission, but I'm really curious what the clouds are going to reveal. So that pass that Da Vinci will do right through the atmosphere and the different cloud layers, what kinds of chemicals will it encounter? What kinds of isotopes? And what does that tell us about Venus's oceans, which is probably the most relevant question to its habitability? Is if we figure out what happened to Venus's oceans, if we figure out what happened to Venus's oceans, and especially like how quickly, if they existed, which isn't a given, but if they existed, how quickly did they evaporate? And is there evidence of that still contained within Venus's clouds? That, I think, is going to open up a lot of astrobiology potential. And I think I'm most excited for that, because there are no clouds like Venus clouds.
Yeah, absolutely. Like I said, Venus is one of my favorites personally. I think we need to know more about the ancient history of Venus, and there's only a few ways for us right now to do that. So those missions are very crucial for that. Our next question is actually one of my more favorite things to think about in general in the current structure of our own solar system. Hendrik Holst has asked if there are any known Oort cloud objects to start with, but then kind of, I guess, maybe more your opinion on whether or not there could be an Earth-sized planet or larger structure out there in the outer solar system that we haven't discovered yet.
Oh, is this Planet X? Which
I mean,
I admit I haven't thought about Planet X since like 2019. So I have to say I don't know that much about it, or even the more updated ideas surrounding it. So I'm sorry, my answer here might be quite short, but I know that the Oort cloud is the birthplace of comets in the solar system, and so we think that many of the comets that we see probably came from there. Although I have to say I don't really know specifics about that either. Oops, you have found a gap in my knowledge. So thank you. Now I'm going to go and like read the Wikipedia page on the Oort cloud and what else is out there. But I mean, there is always the potential for a great discovery.
Yeah.
I just don't know where exactly it will come from, and I think nobody ever does.
Yeah, absolutely. We're always learning more. I can say that with a little bit of knowledge of the Oort cloud, that we have these long period comets that take thousands of years to go kind of into the inner solar system and back out. Their orbits take so long, and so if we start mapping them out, we start seeing this like spherical kind of realm they may be coming from. We have not directly observed an Oort cloud object, to my knowledge, yet, because it is so very far away. I've heard estimates of a half a light year to a light year away, which would be extremely distant, perhaps closer, but that's way further than even the Voyager spacecraft have gone by a long shot. I once did like a back of the envelope calculation. It could be like 1,000 years for Voyager 1 to even get that far out. So that's quite a long distance away. So, but for Hendrik, I would highly say, like, these are the fun questions that make us think. And sometimes we have some answers, sometimes we don't have any. And it's worth going and exploring what we do and don't know currently. Maybe you'll be involved in the next generation of explorers to help us learn even more about those objects. Now, our next question is related to your work on this idea of necrosignatures, or these potential biosignatures of the decay of mass extinctions. Annie C. wants to know what the technology looks like in searching for these potential signatures. Basically, what would we be using to look for potential necrosignatures?
Annie, that is a great question. So I've been standardizing a lot of the work that I've done so far to the different instruments that the JWST, or James Webb Space Telescope, has on it, because that right now is the most precise telescope that we have to study exoplanets. And so I want to know, if there's a signal, would JWST be able to detect it? So that would be like the mid-infrared imager, or the MIRI instrument. And then there's another one that does oh my gosh, I am blanking on the name. But basically, there are two cameras, and they do infrared imaging. Pretty soon, there's going to be the Nancy Grace Roman Space Telescope, which will go out, and that's going to have something like 100 times what Hubble can do in terms of how much it can see. So it's going to be incredible to get just the amount and volume of data that we would need to study different exoplanets. And it's going to be more attuned to look for Earth-sized exoplanets as well. So that's going to be a big improvement as well. And then this is one that doesn't fully exist yet. Right now, it's called the Habitable Worlds Observatory. And when I say it doesn't exist, I mean right now, the planning for this mission and exactly what it can do and what its capabilities are, that is being decided right now by expert teams who have been studying exoplanets for decades, who are the world's experts in detectability and what a biosignature even is. So there's a lot of room for growth in terms of exploration of exoplanets. And I still think the fundamental question of what is a biosignature is not one that has been fully answered yet.
Awesome. Very good answer. I think we have time for maybe one or two questions yet. Let's see how we do. A question from the user Rendering Reality 3D Animations on YouTube considers the potential connections of the ice on Europa, ocean to surface. They would like to know if during your work on studying these microfeatures, if there are any similarities within the spots that you're exploring, like the chaos, to things like ice brine channels on Earth and other features too.
Yes, there are actually, and this is work that Brittany Schmidt, especially, who does extensive field work in Iceland, specifically studying the Jökulláps, which are like these under ice glacier volcanoes, and what the heat from the volcano does to the ice surface on top. So a lot of that field work is directly related to Europa's geomorphology, or maybe like cryomorphology, I suppose, would be a better term for it, but how the surface looks. So I personally haven't done that, and I have to say I'm really jealous, because I would love to do field work in Iceland. But maybe one year I will go out there. So lots of different questions about how ice responds. But we also have to remember that ice on Earth is very different from ice on Europa. It's much colder out there, so ice behaves more like rock out in Europa than it does like ice over here. So the fieldwork that we do here is great, but it's not everything. So we still have to go to Europa, and we still have to see exactly what is going on out there.
Love it. I think we have time for one more question. I'm going to choose this question from Louis from YouTube. Louis wants to know what advice you might give to someone in the UK, and I'll say any country really, who dreams of working for NASA in astrobiology.
I actually know a lot of people who are originally from the UK. I have a couple of really good friends, actually. I have one friend who just began as a professor up at Towson, Alan Jackson. And so what did he do? He came to the United States first as a postdoc, and he just started writing NASA grants with people who were more established scientists, or at least established here in the U.S. And he's just kept doing that now for about a decade, and it seems to have worked for him. Where he's just going, and another way to get here would be to pursue. I don't know what stage of your career you are, Louis, but if you are looking for postdocs, there's a NASA postdoctoral program, which does accept people from really anywhere, almost anywhere. So contact somebody at NASA and put together a really good proposal. But that, I think, and of course, if you're a grad student or if you're looking for a grad student spot, internships, emailing professors, just try reaching out. It's really scary to cold email people when you don't know them. But if you want to know more, then again, just trust yourself, because you know what you like, and grad school and science and life really is just a journey of self-discovery. So go for it.
Fantastic. Thanks, Louis. Thanks to all who are watching. We love the questions you were asking. I didn't get to all of them. I apologize for that. If you'd like to learn more about Dr. Noviello and her work, and maybe even find ways to ask her your own questions, you can visit her website at jessicanoviello.phd.sh and learn more about her there, all of her current research. She's studying so many different cool topics, from Itokawa and a Venus concept mission and exoplanets and possible necrosignatures, going out and digging for dinosaurs and all of these cool things. So, Jessica, it's been so much fun having you on the show and here to answer some of our questions. Thank you so much.
Thank you so much for having me. Sorry we didn't get to all the questions.
Yeah, I mean, that always happens. There's so many awesome questions about astrobiology, from the questions in our chat on YouTube to the questions that people will reach out and cold email us with and ask us questions. And I know a lot of us do try our best to answer when we can, even though we are very busy. So please understand that sometimes we can't answer right away. If you'd like to learn more about the PAWS Professional Advancement Workshop Series, again, you can visit nexus.info/PAWS. That's nexs.info/PAWS. You can learn more about PAWS there. I highly recommend you check out Dr. Noviello's website. For those who want to learn more about things going on at NASA Astrobiology, like episodes of our show, upcoming events, things like the PAWS workshop and others, please sign up for the newsletter. It's the email that comes from NASA Astrobiology. It announces all kinds of things you can learn about and study and explore with us through NASA Astrobiology in the program. So, Dr. Noviello, thank you for joining us. To our audience, thank you for joining us, everyone. Until next time, remember to stay curious.